Wait a minute. Oh, hello. Okay, welcome back to Monty's Python Show for our latest tutorial video. In this video, this is going to be a code along tutorial that you can work alongside with me, and it's going to be about data analysis using Python. Specifically, we're going to be taking a look at an old concept in economics called Okun's law. So what's in this tutorial? We're going to talk about ways to get data for a research project that you're working on, and specifically I'm going to show you how to access data files from the FRED database. This is a great database of tons of global economic data. It's provided by the Federal Reserve Bank of St. Louis. I'm going to introduce you to using pandas, and specifically we're going to be working with dataframes. So we're going to learn how to get data from the CSV files that we download from the FRED database into our Python project and into pandas dataframes. We're going to learn how to clean up and prepare the data for analysis, and then I'm going to show you how to do some basic statistical analysis of the data. We're also going to be working with the Matplotlib library and specifically the pyplot module, and we're going to be using that to make different types of charts, XY scatter plots and time series line chart. So a little bit more about our analysis topic. We're going to be talking about Okun's law, which is really not so much a law. He proposed it as a law, but it's really considered a rule of thumb because it's an empirical question. But Arthur Okun published this research in 1962 where he demonstrated a relationship between short-run unemployment and economic output, and specifically that declines in economic output are associated with increasing unemployment. Now that seems pretty intuitive, and the data certainly does support that, but the specific claim that Okun made that was known as his law is that a 2% change in real gross domestic product results in a 1% change in unemployment. And he also posited that that relationship was an inverse relationship. So a 2% decline in real output would result in a 1% increase in the unemployment rate. There's been lots of research and follow-up on this concept. In some circles, this concept is considered controversial. It's a little bit simplistic because there are obviously many factors that affect employment and economic activity, and this is a very simple model of the world. But nonetheless, it is a very interesting topic and serves as a good backdrop for our project. So here's what we're going to do today. So there are a number of different versions of Okun's law, and we're going to be taking a look at the one that's known as the change version. That is the one that is the simplest to find data for and to estimate the parameters and to interpret. And the specific equation that we're going to be looking at is the change version of Okun's law, which is shown here, which says that the change in the unemployment rate at time t is can be described by a linear equation equal to alpha plus beta times the change in real GDP. So the DUT is the first order change in the unemployment rate, and DYT is the percent change in real economic output at time t. And we're going to use Python to estimate the parameters alpha and beta. But if you think about the concept that Okun put forth, we would expect alpha to be positive, because if you look at that equation, alpha represents effectively what you would expect the change in unemployment to be if there were zero growth in the economy. So if the economy weren't growing, you would expect that unemployment would rise. Well, you certainly wouldn't expect it to be negative. Maybe it could be zero or close to zero, but you would not expect it to be negative. On the other hand, the beta parameter, which is the slope in this line, we would expect to be negative because an increase in economic output you would expect to be associated with a decline in the unemployment rate. And if you think of Okun's specific claim that a 2% change in economic output is associated with a 1% change in the unemployment rate, then you would expect that beta parameter to be somewhere in the vicinity of negative 0.5. To start, we need to go ahead and get our data. And we're going to use the FRED economic database, which is a free source of data provided by the Federal Reserve Bank of St. Louis. And if you just go to fred.stlouisfed.org, it will take you to the screen that I'm on here. For this, our initial analysis, we're going to need two different series from the FRED database. We're going to need the real GDP and the unemployment rate over time. So let's go ahead and search for those here. I'm going to search for FRED for real GDP. And so we see at the top here, real gross domestic product, billions of change, 2017 dollars. So that is just the basis for which they are standardizing the price to make this a real gross domestic product. In other words, this is inflation adjusted, and it's also seasonally adjusted for taking out seasonal effects on the data series. So I've clicked on that, and it takes us to the page for that particular series of data. And there's a download button here in the top right. Go ahead and click that download button. And we want CSV. That is the form of data file, flat data file we're going to use for our project. So click there. And go ahead and put that file wherever you are creating your project. And I'm going to call this file gdp.csv, and I've created a folder called economic analysis. I'm going to go ahead and save it there. And the next series we need is our unemployment rate, seasonally adjusted. So I'm just going to type in the search here, unemployment rate. And here we go, percent monthly seasonally adjusted. That will do great. Let's go ahead and click there on that unemployment rate. And once again, we're going to click on the download button and CSV. And I'm going to call that unemployment.csv. Save that in my economic analysis folder. Okay, so we've downloaded our two CSV files that we need for our analysis. Make sure that the files, the CSV files, are in the same directory as the Python project that you create, because the code that I'm going to show you is going to be built in such a way that it's going to look in the current working directory to find those files. I'm using Spider for this, but you can use any development environment that works for you. Just make sure that you have access to the following packages and modules. We'll need Pandas. We'll need the OS module, and we will ultimately use the Matplotlib to create our charts. Okay, so let's go ahead and get started. The first thing we want to do is import all of our external packages, libraries, modules. So import packages, and from the OS module, I want to import two useful methods. The get CWD, that will look up our current working directory, and then the path. And we're also going to import pandas as PD, and that's good for now. Import pandas as PD is kind of an industry standard way to do it, just like import numpy as NP. So doing it that way just makes it easier if you're looking at someone else's code that's using pandas to have sort of a common language that PD represents the pandas library. Okay, so the first thing we need to do is get the path and file name information for our two data files. And this is a good way to do it if you have, especially if you're working with directories in Windows and some of your folder names have spaces in the names and things like that. It can sometimes be difficult to access those directories. And also if you have really long paths to files, this can be an easier way to do that. So we're going to set file and path data. Okay, so the first thing I want to do is get the current working directory, and I'm going to save that in a variable CWD and set that equal to, now we're using the get CWD method from the OS module. And I'm going to go ahead and type in my two file names. So I'm going to call my unemployment file up file. And that file name is, I saved that as unemployment.csv. Make sure you include the .csv as part of that file name. And then my GDP file was saved as gdp.csv. The join method from the OS path to create the path and file name in a pretty foolproof way. This works really well. So I'm going to define a variable called updata. I'm going to set that equal to path.join, and we're going to join together the current working directory and our file name. So upfile is the file that corresponds to the updata, and the GDP data, set that equal to path.join, and again CWD, that's the directory path, and the data file is GDP file. Okay, so we've set up our path and file name information to access those files. Now let's go ahead and read those into our Pandas data frames. And we are going to use the read CSV method, which is in the Pandas library. So I'm going to create a data frame for my unemployment data called up. Set that equal to PD, that's my Pandas alias, dot read underscore CSV. And then I'm just going to pass the up data variable. And so it will look in that path and file name. It will read the contents of that CSV file and bring that into a data frame called UP. And we'll do the same for GDP. Set that equal to PD dot read CSV. And that path and file name is GDP data. Okay, so let's go ahead and run this code. Make sure we have no errors. Okay, it looks good. And let's just take a look at what we have so far. So I'm going to print up here in my console. And okay, so you can see we got some data. We have 3 columns of data. We have an index column, which is just in integers. We have a date column. So we can see our data for unemployment rate starts January 1st, 1948. And then we have the unemployment rate, which is, it's a percentage rate, but it's multiplied by 100. So 3.4 is 3.4%, and that column name is unrate. And we can see we have 910 individual data points, 910 rows. All right, and let's take a look at our GDP data frame, make sure that looks good. Okay, same, we have 3 columns. We have the index column, we have a date column, and we have our GDP C1. So that is a nominal, it's the real dollar amount of GDP as of that date. And we can see that the GDP data goes back a little farther, goes back to 1947. So we've got a little inconsistency in our data time period, but we'll solve that in just a minute. And we can see that we only have 307 rows of GDP, even though it goes back farther, and that's because the GDP data is quarterly. So you notice that our first value is from January of 1947, and then the second data point is from April. So the GDP data comes out every 3 months, while the unemployment comes out every month. So we're going to have to do a little massaging of our data to get the 2 data frames to line up. And so the first thing we're going to do is we're going to create a main data frame. We're going to do that by merging our 2 data frames together. So merge the 2 data frames, and we're going to call it DF. So if you're just working with a single data frame, it's common to just refer to it as DF. And we're going to set that equal to PD, and we're going to apply the merge method. The first 2 arguments are going to be the 2 data frames that you want to merge. So we're merging up and GDP. And then there is a how argument, and we are going to do an inner merge. So how is going to be set to the string inner. And what an inner merge does is it only merges the data that is the intersection of the two data frames. So if you think of like a Venn diagram and where the 2 circles intersect, that is the data that will be kept. So it will get rid of any data that is excluded in one or the other data frame. And let's go ahead and run that. And now let's look over in the console and let's take a look at what DF looks like. I'm going to print DF. Okay, so we can see we've got an index column. Now we've got a single date, and for each date we have 2 data points. We have our unemployment rate and we have our GDP nominal amount. Okay, so we have our data for the 2 series in our data frame. And the next thing we need to do is we need to change that data, manipulate the data to fit the type of analysis that we want to perform. So before we do that, let's just take a second look at the data frame that we created in DF. So we can see that we have both our unemployment rate, the unrate column, and we have the real GDP in dollars. And you notice that when we merged the 2 data frames, the unemployment rate dropped out some of its data, because if you recall, the unemployment rate had monthly data and the GDP had quarterly data. So when we performed the merge, we did an inner merge, And the inner merge only brings together the data that they have in common. So it only brought together the common date information. So that's good because we want to make sure when we do our analysis that we're comparing the proper period for unemployment rate and the GDP rate. Now, the actual analysis when we check, do the review of the Okun's law equation, is the Okun's law equation, we're looking at the change version of that equation. And so what that means is we need to look at the year-over-year change in the unemployment rate and the year-over-year percentage change in the real GDP. And so, in other words, if you look at the data that we have, it's quarterly. So we're not going to be calculating a sequential change in these series. We need to look at the change over 4 periods. So for example, when we calculate the January 1949 change in the unemployment rate, we're actually going to be looking at the change in the rate 4.3 versus the rate that was 4 quarters prior, which would be 3.4. So, and the same goes for the GDP percent change. We're actually going to be looking at the percent change year over year, which means we have to compare the level to the same quarter in the prior year. So in this case, on the GDP percent change, we would be looking at the percent change from January 1948 to January 1949. So I'll show you how we will do that. And we're just going to add new columns to our existing data frame with this new information. So we're going to add the change data for each series. Okay, so the way you create a new column in your data frame, it's very similar to creating a new key in a dictionary. Just the name of the object, df, and then the name of the column. And so we're going to call this, this is for our unemployment, we're going to call it unemployment change. And we're going to set that equal to df, and we're working with the unrate column in the existing data frame df. And we're going to apply the diff method. Now the diff method will accept an argument and that will allow us to specify the difference between which periods. So we actually want to specify the difference in the data for each 4-period series. So we're going to set periods equal to 4. So this will calculate the change in one data point versus the same data point 4 quarters prior. So in other words, the same data in the prior year, the same quarter in the prior year. Okay, so that will calculate our change in the unemployment rate year over year. Now let's specify our GDP, and we're going to do percent change in GDP. And we're going to set that equal to our object data frame. And now we're looking at the GDP C1 column. That's the column we want to look at for our analysis. And we're going to apply the percent change method with the same argument, periods equals 4. Now you might be wondering, why are we looking at the absolute change in the unemployment rate versus the percentage change in the GDP rate? You certainly could look at the percentage change in the GDP, but to match the common way that this analysis is done, we're doing it this way. And if you think about it, the unemployment rate is already itself a percentage, and so looking at the percentage change in a percentage is just a little bit more difficult to interpret what that means. And it also will inflate the numbers and inflate the standard deviation of that time series, and make the individual parameters that we're going to estimate in a regression model more difficult to interpret. So the typical way this is done, when you have a percentage already, like unemployment rate, we'll just simply look at the absolute change in the percentage unemployment rate. Okay, so now we have our 2 changes. Let's go ahead and run this and take a look at our resulting data frame. Okay, so you'll notice in our resulting data frame in the console, we have our new columns. We have our unemployment change, and we have our GDP percentage change columns. But since the change and the percent change are taking a 4-quarter lag, if you will, looking at the data 4 quarters prior, the first 4 data points are unable to calculate a change for. So we have, that's what that NAN data means. It means that it just couldn't calculate it because there was not any data to calculate the change against. So we can go ahead and drop those from our data frame. We don't need that data. We also won't be needing the unrate and the GDP C1 columns anymore because we'll be working with just the change. So let's go ahead and clean up our data frame DF to just include the data that we want in it. So let's clean up the data frame. Okay, and the first thing we're going to do is let's go ahead and drop the columns that we don't need. So we're going to use the drop method, df.drop, and drop takes the first argument is the columns that you want to drop, and so columns, and you can pass the argument as a list if you have multiple columns you want to drop. So we're going to make a list of the names of columns. So we're going to drop the unrate column and the GDPC1 column. And we don't want to make a copy of the data frame. We want to do this in place. So there's a second argument, in place equals true. Okay, so in place equals true. It means it's going to change the data frame DF. DF is mutable, and so we're going to change it in place. Okay, so that will drop off those two unwanted columns. And then let's go ahead and drop out the first 4 data points, the first 4 rows. So again, we're going to do df.drop. But instead of dropping columns, we're going to be dropping rows. And the rows are identified by index. And the indexes, in this case, are all integers. Now, you could have an index that's not an integer base. Like we could set up this data frame to have date as the index. And so if that were the case, you would actually specify the dates that you wanted to drop. But in our data frame, the index is an integer. So we're going to set index equal to, and then we'll make a list of the rows we want to drop, 0, 1, 2, and 3. So those are the first 4 rows. And again, we want to make this change in place. So in place equals true. Let's go ahead and run that and take a fresh look at our data frame. Okay, so now we can see our data frame has only the change data in it, and we eliminated the first 4 data points. So now our data starts in January of 1949. That's the first quarter for which we have change information. Okay, there's one last thing we want to do to clean up our data frame, and that is we want to change the index to be the date column rather than the integers. And when you're working with time series data in Pandas, it is often a good practice to go ahead and set the date column to be your index. It makes it easier to slice, index, filter, drop items from your database when you can specify ranges of dates or particular dates, because that tends to be the variable that you're working with in terms of controlling the data. So there's 2 steps to this. First, we need to change the date column from strings to datetime objects. So the data that we downloaded in the CSV files, that date is actually a string currently. So here's how we can change that to a datetime object. So specify the data frame df and then date, and we want to set that equal to pd.to_datetime, and then specify again df date. So we're just reassigning the series date to itself, but we're changing it from a string to datetime. Okay, and then now let's go ahead and set the index to the date. So it's df.set_index, and the argument is date, and we want to make that change in place. So in place equals true. Okay, so those 2 lines should change the date to datetime and then set it as the index. Let's run that code and make sure it works. So now if I print out my data frame, I can see that in fact date is the index now. We don't have that integer column anymore. Okay, so now we have the data frame set up with all of the data that we need to do our analysis. We've got it cleaned up and ready to go. Now we need to write the code to perform the analysis and to create the visualizations. And the way we're going to do that is we're going to create a separate module and import that code into our main project. And the reason for that is that we don't want to litter up our main project with so many lines of code that it's difficult to follow what's going on, and it will make it cleaner and easier to understand when we're actually performing the analysis and looking at the results. So let's go ahead and create a new Python file. We're going to call this file Analyzer. And we want to make sure that we save this in the same directory as our main Python project and where our CSV files are. Let's keep all the files in the same directory. That way we can have no problems importing it into our Python project. Okay, so there are basically 3 different functions that we want to create in our Analyzer module. We want to create one that will generate a time series chart, so a line chart of the data points over time. We want one that will generate a scatter chart or an XY plot of the data so we can graphically look at the relationship between the two data fields we have. And then we want to create a function that will fit a regression line to the data so that we can estimate the parameters of the Okun changes version of the equation. Okay, so let's go ahead, and the first thing we want to do here is I'm going to start at the bottom of my module, and I'm going to add the if name equals main idiom. That way we can test our functions that we create in the Analyzer module inside of the module before we import it into our main project. And by testing the code inside of that idiom, that code will not run when we import it into our main project. So I'm going to write the following line: if underscore name double equals the string double underscore main. And here's where we're going to write our testing code. I'm just going to put pass for now. So the first function we want to create is our time series chart. So we're going to define a function called time series chart. And time series chart is going to have 3 arguments: dates, and then series 1. So the dates in series 1 will be mandatory arguments. And we're going to have a second series that will be optional. So we're going to set the series 2, and we're just going to set that equal to an empty pandas series. So pd.series, and then, oops. So a empty brackets inside of empty parentheses, and end parenthesis there, colon. Okay, and we need to go ahead and import a few things also. So let's do that now. We need to import pandas as PD. And we will also import matplotlib.pyplot as PLT. So, okay, so our time series chart, let's go ahead and create the plot and axis data. And since we have an optional data series, we're going to use an if-else statement inside of this function to control which plots we create and what the chart title is going to be. It's going to be dependent on whether or not there is a series 2 passed. So let's comment this: create series 1 plot and axis data. And so let's call that pyplot module plt.plot, and we're going to plot dates and series 1. And let's make the first line color blue. And let's set marker equal to none. And let's add a label. And here's something that's kind of cool. Since we'll be passing pandas data frame series as the arguments when we call these functions, our function will be able to access the name attribute of those series. So we actually don't have to type that data in separate. We can access that attribute of the series that gets passed as an argument to the function. So label will be equal to series1.name. Okay, let's go ahead and label the x-axis. plt.xLabel will be date. Now we could also access the name of the index, but since we made dates as a mandatory argument for this function, there's no need to do that. We know that's going to be date in that data, so we could just call that date here. Okay, so now let's create the series 2 plot and axis data if it exists. Okay, so if not series 2 dot empty, that's how we're going to do that. So if series 2 is not empty, then we're going to specify a secondary axis. Since the two data points that we have, one of them is quite a bit more volatile than the other, we want and has a wider range of outcomes. We want to create two different axes so that we can easily see these charts, the line charts overlaid next to one another. So we're going to create a second axis, AX2, and that is going to be equal to PLT dot GCA dot twin X. Okay, so it's going to create an alternate axis. And then let's go ahead with that AX2 object plot, just as before, dates. This will be series 2. Set the color equal to red. Marker will be none, and the label will be series 2 dot name. And I just realized we made a mistake up here. This should say series 1 dot name, not series 2. Okay, just take a quick look. That looks good. Okay, and if there is a series 2 data, we want to have a slightly different plot title. So we'll specify PLT dot title, and it's going to be set equal to the following formatted string: series 1 dot name dash series 2 dot name, and then let's say over time. So that will be the title if there is both a series 1 and a series 2 data. Okay, and so now we're outside of our if. Let's go to our else, and if there is no second series, then PLT dot title will simply be series 1 dot name over time. Okay, and the final thing we need to do is add a legend and show the chart. So PLT dot legend and PLT dot show. Okay, so let's test that out and make sure that our function works. So down here inside of our if name equals main idiom, let's write some code to test that. So we need to go ahead, let's create a little data frame here. So I'm going to define a variable called data, and I'm going to set that equal to a list of tuples. So the first tuple, let's see, it's going to have some, say it's got a date 1991 01-01, and then let's give it X data 3 and a Y data 1, and let's do another entry for 1992-01-01, and this will be let's see, data 2 and 3, and add a third 1993-01-01. Boy, I can't type. And this will be data 1 and 3. Let's say 2 and 3. Let's go 1 and 3. Okay, I'm going to change this to 2 and 2. So we're just plotting a line. Okay, that looks good. And let's create names for our columns. So we've got a date column, and then we've got, let's just call it X, and we'll call it Y. And let's create a data frame from that, call it df equals pd.dataframe. And so data is the data, and columns equals COL. I think, well, I see that's an error there. Dates, and this should be series 1 name. Ah, I see. This should be GCA, beginning and ending parenthesis there. Let's try that. There we go. Okay. So a little typo there. Sorry about that. Okay, so it did in fact print both series, and let's see our chart. This says x equals y, and so let's change that in the code. This equal sign right here should be a dash. Let's rerun that. Okay, x and y over time looks good. We've got the date, we've got a label, we've got 2 different axes, and let's just test, see what happens if we do not pass the y argument as our second data to plot, and make sure that, okay, so that worked. That only plotted the x data on the line chart. Okay, good. So there's our time series chart function. That seems to work well. So now let's go ahead and create our next function, which is going to be, we want to create a scatter plot. So we're going to define scatter, and scatter will have 2 mandatory parameters, x and y. Here's how scatter is going to work. So we're going to define another function below that is going to estimate the parameters of the regression line, and we're going to call that here, but I'm just going to leave it blank for now. I'm just going to put a comment, invoke the line fit to get parameters, because we want to print the fitted line on top of our chart. I'm just put pass for now. Okay, let's continue on with the scatter plot. So let's go ahead and plot the x and y data on the scatter plot. Okay, so it's plt.scatter is the type of chart, and our data is x and y. Let's make the color again equal to blue, and let's make the marker an x. Okay. And let's go ahead and then format the chart area. So plt.x label. Again, we can access x.name for that, and plt.y label will access the name attribute from y, again because those are pandas series, data frame series, and we want to show a legend, and plt.show. Okay. So now let's go down here to our test, and let's add the scatter chart, and we're going to pass from our data frame the x value and the y value. And again, these are mandatory this time, so you have to pass both series in order for that to work. Let's run this and see if that works. Okay, so that worked. That plotted our x and y data as a scatter chart, x data down here on the x-axis, the y data here, and blue axis. Okay, so our scatter chart, we're going to come back and build it out a little more in a second, but first we need to go ahead and create our analysis function. And our analysis function we're going to call line fit. So we're going to define a function called line fit, and line fit takes 2 mandatory arguments, the x and the y data. Okay, so what line fit is going to do is it's going to estimate the coefficients of the linear regression, and it's going to return that information back to the function call. And there are many different packages that you can use to actually implement regressions, but I wanted to keep this this tutorial simple in terms of accessing different packages, because I'm not sure what all packages you might have access to. But there are packages like SciPy, Stats Models, NumPy, and sklearn that you can use to do regression analysis. But I thought it might be a good exercise to actually do this the old-fashioned way and calculate the parameters ourselves. And that might give you a little insight. Maybe you didn't know that you could calculate those coefficients by hand or just formulaically. And also it will give you a little access to some of these descriptive statistics that you can access through the Pandas module. Okay, so a long way of saying we're going to do our own regression analysis. We're not going to import a package for that. We're going to rely on the summary statistics that Pandas provides in order to estimate the coefficients. Okay, so here's what our line fit model is going to do. So first we need to calculate some statistics. So we're going to calculate statistics using Panda methods. And so we're going to calculate the mean of the x variable. So this is just the arithmetic average of the x variable, and that's going to be equal to x dot mean. So the Pandas has a mean method that calculates that. So x dot mean will return the mean of that series. And let's calculate the mean of y to be equal to y dot mean. And then we need the standard deviation of x, and that is equal to x dot std, and same for y. Okay, and then there's one more thing we need, which is the correlation coefficient. We're going to call that r, and y dot core, and pass x as the argument. You could x dot core or y dot core, it doesn't matter. Correlation measures the degree to which two random variables move together, and it's a statistic that will fall between -1 and +1. So positive numbers mean the two variables tend to move together, and negative means they tend to move inversely. And the larger the number, the higher the degree to which they tend to move together. So a 1 is like perfect positive correlation, and -1 would be perfect negative correlation. Okay, so we have our base statistics. Now we can go ahead and calculate the coefficients of our linear regression. So we're going to now calculate the slope and the intercept and the r squared. And I'll explain that in just a second. Okay, so the slope we're going to call b. That is simply equal to the correlation coefficient times the ratio of the standard deviation of the y variable divided by standard deviation of x. So the ratio of the standard deviations times the correlation coefficient actually gives you the slope of the linear regression. And then from that, using that, we can also calculate the intercept, the alpha coefficient, which equals the mean of the y variable minus the beta times the mean of x. And our r squared, which we're just going to call r underscore sq, is just equal to r squared. And so the r squared is a statistic that will tell you what percentage of the variation of the dependent variable is explained by variation of the independent variable. So a higher r squared, the better. It's a number that will range between 0 and 1. Okay, so last thing we want to do with our line fit function is let's just return that information. And we're going to return it as a tuple. So we're going to do the slope first, the intercept second, and the r squared third. Okay, so let's test line fit down here before we add it back into our scatter plot. So let's call the line fit function, and actually we're going to print this, because it's returning a value, line fit, and so again, data frame x is our x value, and data frame y is our y values. And let's run that and see what prints. Okay, so we can see we got a printout here. It printed -1 for the slope, 4 is the intercept, and 1.0 is the r squared. And that makes sense because if you look at the data, you can see that the data that we created in this data frame is is actually a -1 correlation. It's the x values are 3, 2, 1, and the y values are 1, 2, 3. So you can see that they're perfectly negatively correlated, and it is a straight line with a slope of -1. Okay, so now let's go back up to our scatter function, and we want to add the code where we are going to invoke the line fit function to get the parameters. So since it returns a tuple, we're going to access the b, a, and the r squared from our line fit. And here we can just pass this as x and y, because x and y were passed into the scatter function already. We're going to add something to our plot. We're going to plot the best fit line on there, and we're also going to print out the actual best fit line function on our chart as well. Here's how we're going to do that. So we're going to create a variable x_fit, and it's going to be a Pandas series, so it's going to be equal to pd.series. And so we're going to just take the lowest x value and the highest x value as the extreme ends of this series. So x.min, and that's a method, so we have parentheses on it. And then the upper bound is going to be x.max. Okay, so that creates the x data for our fitted line, and then y fit is going to be equal to our function. So we have our variables a, b, a and b, so it's equal to a plus b times and x_fit. Okay, so that will use the equation to calculate the data to plot on the y-axis, against the y-axis there. And one other thing we want to do is let's plot that, plt.plot. So the x fit is the x data, the y fit is the y data, and we'll make this different, so I'll make it red, and we're going to give it a label equal to the following formatted string, and we're going to call that so y.name equals then the value of a, and let's format that 2 decimals, plus b formatted 2 decimals times x.name. Okay, I think we got it. So let's go ahead and run this code and see if it prints out the XY chart with the data on it. Okay, so it worked. So you can see our chart now has a fitted line going through the 3 data points, and it's also in the legend here, it is printed the actual regression equation. So 4 was the intercept and -1 was the slope of our fitted line. And so that looks good. Okay, so we've got everything completed in our analyzer module. Now let's go back to our main project and import and use this data. We need to go ahead and import our analyzer module and the functions from that module that we want to use. So I'm going to go back up top to my import packages and add the following import: from analyzer import scatter, line fit, and time series chart. Okay, so we now have all the code set up and ready to go ahead and do the analysis that we want to do, our data analysis. We have the data in our data frames. We have it edited the way we want it. Now we're just ready to use the analysis tools from our. So the first thing we want to do is check to see if our model and our data make some sense against some existing studies. And there was recently, within the last 15 years, an update on the Okun's Law regressions done by the Federal Reserve Bank of Kansas City. And they published their results in a paper. So let's try to replicate their results and see if we get answers that come close to what they have. And that will give us some confidence that our data and our models are set up properly. Okay, so here is the relevant page from the research report that was done by the Federal Reserve Bank of Kansas City. And they did an update that included data from 1949 to 2006. It doesn't say in the footnote exactly when the data ends, but I know this paper was written in 2007 or published in 2007. So I'm just going to assume that the data runs through the end of 2006, but we might be off by a quarter or two, so that shouldn't make too big of a difference. And here is the results of their analysis. So they ran the regression, and they got the intercept of 1.2% and the slope to be negative 0.35 during that time period. So that that slope value is a little bit less than, in magnitude, a little less than one would expect based on the original Okun research, that you would expect this to be closer to around 0.5%, but it's still within a reasonable range. Okay, so how can we change our data to replicate that Kansas City? Okay, so to evaluate our data and compare it to the Kansas City Fed data, we need to go ahead and make a copy of the data frame and filter out just the dates that we want. So let's make a note here. We're going to compare data to recent research from KC Fed. All right. So step one is let's create a new data frame called df_KC. And we're going to set it equal to. Now we're going to apply a filter to the index of our original data frame df, but we want to make sure we apply the filter to a copy of the data frame so we don't actually change the original data frame. So here's how you do it. df is the name of our main data frame, and then inside of square brackets we want to set df.index and set that to be less than or equal to pd dot to date time, and then the argument to the to date time method is going to be our date 2007-01-01, and then at the end outside of the square bracket dot copy. So we're going to make a copy of the data frame and then filter it. Okay, so we're not affecting the original data frame. All right, so I'm just going to run that real quick and let's take a look at the data frame. All right, so in my console, let's take a look at df_KC. All right, so there you go. You see that our data now ends in 2007. So comparing that to our main data frame df, notice it ends in 2023, July. So we're going to first run our analysis on this KC dataset, and let's see if we get something close. So let's use our scatter function. Scatter df_KC, and our X item is GDP percent change, and our Y item is df_KC UPCHG. So you definitely want to make sure to get accurate results, make sure you're pointing at the right data frame, df_KC. All right, let's run that and see what we get. Okay, so looking over in my chart window over here, you can see it did print out our regression analysis on our scatter plot. So looking at our coefficients, we got 1.3 for the intercept and negative 0.36 for the slope. And so that compares pretty favorably with the research report. They got 1.2 and negative 0.35. So that's actually pretty close. Their data might be slightly different, and maybe it doesn't go all the way through 2006. It doesn't specify exactly when their data ended. So that probably explains that small difference. But we're close enough, I think, to suggest that the data that we have and the analysis that we're performing is probably good. Okay, so now that we've done that, let's go ahead and run the analysis on our entire data set. And I'm just going to change what we've already written here. So let's change this note. So rather than comparing the data, I'm going to write run analysis. And we can get rid of this data frame underscore KC. We don't need that anymore. And then we're just going to change this scatter function to run it on the main data frame, df. So get rid of the underscore KC. So scatter, our X data is from the df data frame, GDP percent change, and from the df data frame, the unemployment change is our Y variable. I'm going to delete the chart that it was made before and just clear out my console and run this analysis. Okay, so this is our analysis for the entire time, looking at it in our chart viewer. And you can see that we do get results that seem pretty close to what we expected for the entire analysis period. So if you recall back in the original presentation, that we expected the slope to be negative and somewhere in the vicinity of maybe a 0.5 percentage point if it was consistent with Okun's interpretations of his analysis. And so it looks pretty good. And then just looking at the data, you can see that there are some fairly large outliers. There's one reading here that's a big negative GDP and a big increase in unemployment. That's probably COVID. And then there, at the other end of the spectrum, there's a big decline in unemployment and a large GDP percent change. That's probably recovery from COVID. But those two extreme data points, if there was just one of those, we might consider removing it from the data because it may be skewing our line fit because there's some outlier data. But it looks like the data is relatively well distributed around the line. So it doesn't seem like that outlier data is probably having a large impact on our analysis. Okay, so we've done our scatter chart analysis. Now let's take a look at the time series of the data and see if that gives us any information about this relationship. So we're going to use the time series chart function that we used, that we created in our analyzer module. And so we'll pass to it, the first argument was the dates. So in our case, it's df.index. That is the thing that has the dates in it. And let's plot our first data series, which is going to be the GDP growth rate. So GDP percent change. And then our other series, which is our unemployment rate changes from data frame UPCHG. Okay, so that line right there calls the time series chart function, and that should draw a time series chart. Let's run that. Okay, so that worked, and you can see over here in the chart explorer, the red line is the unemployment change, and the blue line is our GDP percent change. And for some reason, the GDP percent change legend is not printing, but that's okay. Since there's only two series, we can figure out which one is which. And looking at this chart, we can see that this does also seem to support the idea that there's a inverse relationship between the unemployment rate and real GDP growth. So looking at some of these data points, you can see in times where the blue line here is dipping down is often at the same time when the red line is going up. So they are clearly moving inversely. You can see it there. And you can see it really clearly here in 2008, 2008 and 9. So you see this, the blue line, so you had negative GDP growth pretty significantly there, and you saw a big increase in the unemployment rate. And then you can also see it here in the COVID data in 2020. So the first hit here when the economy shut down, you see the big negative move in GDP, and then the contemporaneous rise in the unemployment rate. And then you can see as that starts to unwind itself throughout the remainder of 2020, we saw a bit of a comeback in the unemployment rate, and then come back down in the unemployment rate and a rise in GDP. Okay, there's one last bit of analysis that we want to do for this tutorial. Let's go back to our original formula. And so this is the formula, the regression line that we estimated with our parameters in it. And so if you look at this formula, on the left-hand side, we have the change in the unemployment rate. And on the right-hand side, we have the real GDP growth rate. Now, if you look at this, this implies that we could figure out what growth rate at which you would have a 0 change in the unemployment rate. So in other words, what would be the growth rate that would be consistent with a stable unemployment rate? And so we've done that down here. Just set the left-hand side equal to 0 and then solve for dy. And I'm calling this dy stable. So this is the real GDP growth rate at which you have stable unemployment. And so if you rearrange this equation and solve for that, you get that dy stable is equal to approximately 3%. So this is saying that based on our model, at a roughly 3% GDP real GDP growth rate, you should have on average stable unemployment, meaning it doesn't go up or it doesn't go down. It's no change in average. Okay, so let's go back then and take a look at our data, look at one more piece of information before we finish up. So I want to calculate, given that we have the growth rate in GDP since 1949 to the present, what is the average annual year-over-year real GDP growth rate? And so we can print that out. So I'm going to print, and then we're going to go into our data frame, df, and we're going to look at GDP percent change. And we're going to print out the mean of that series. So that's the average year-over-year real GDP growth rate in our sample. So let's run that. Okay, and if you look over here in my console, you will see that actually on average, real GDP growth rate over this time period has been right about 3%. So that might be a coincidence, but it could also be on purpose. So if you're familiar with the Federal Reserve Bank, the Federal Reserve has a dual mandate to target certain things, and what they look at is they try to have full employment, so as low of unemployment as possible, while achieving the highest sustainable growth rate in the economy. So they're actually targeting, as a matter of policy, positive growth and stable employment. And so it's very interesting that the growth rate that our model implies you would need to have over time to have stable employment is very close to the actual growth rate in the economy over time. So again, our model doesn't prove that that is necessarily what's happening, but it is an interesting observation, and it shows you how to some of the types of analysis you can do with the data and using the tools that are in Pandas and Matplotlib. Okay, so that does it for this episode of Monty's Python Show. I hope you enjoyed this data analysis video. Hopefully in this tutorial you got a good sense for how to get data and bring it into Pandas data frames, manipulate that data, and then do some basic data analysis, including charting and some statistical analysis. Coming up, we're going to do more data analysis tutorial videos on specific topics, so stay tuned for that. And until next time, wipe the crumbs out your beard and Python.